argument, so I thought I'd first clarify. I had the advantage of going right after Jim, so position matters here. 5 minutes ago, Jim said the moral should be that the whole argument does not show that we must adopt new forms of relativity theory. If anything, it emphasizes the expressive resources available in the structure in G. I completely agree with the statement. In particular, I like the use of this word expressive, and so I'll sort of mention towards the end why I think that's a nice term. And so if this is what you really care about, I think we must basically agree. Maybe this is going to be a semantic comment about some minor disagreements, so we'll see. The other thing I wanted to say is, point of preface, is I've been thinking about things to do with space-time around Jim and Irvine people for a long time, so it's a pleasure to have you all here. Thank you so much for coming. Now, see, you flashed my supervisors up, and now I flash your supervisor. There's this old philosophical question you see, philosophers speaking about for a long time, Putnam, Davidson, many other people. You have some picture or piece of language like this portrait, and you ask, what can it represent? Or you might ask, what can it not represent? And you might ask further questions about how it is that it comes to represent things, what's required of such a representation relation. As philosophers of science, we've tended to focus more on some specific piece of mathematics. What can a given piece of mathematics represent, say, as it appears in a scientific theory? But also in pure foundations of mathematics, people ask this sort of question. And what can it not represent? I want to just highlight a forthcoming paper of my co-organizer, James Nguyen, on this topic, drawing these together, showing how these two questions are deeply related. And now today, we're going to be even a little bit more specific and ask things like, let MG be a Lorentzian manifold. What can it represent? What can it not represent? And these aren't being asked for the first time. So if you look at the text of the 1987 paper that we were just discussing in the last lecture, it's largely about representation. So this is the first sentence in the section called What Represents Space-Time? They say what structure in space-time theories represents space-time? And pose this as sort of the central question to be answered and to try and learn about in the context of relativity theory. Now, to get a handle on that, we're not going to be able to answer that question in full generality, but we can pose a few conditions on representation and sort of consider whether or not they're true. In this paper, we pose Leibniz equivalence, all right, that isometric spacetimes represent the same physical situation. So that's another quote from Ehrman and Norton, again using representation language. We could pose the denial of Leibniz equivalence. Some isometric spacetimes do not represent the same physical situation. Okay. What's sort of more commonly debated is, we could call it even strong denial of Leibniz equivalence, that all non-trivial isometric spacetimes do not represent the same physical situation. And then Norton and Ehrman posed this argument in order to try and evaluate some of these positions. Jim went through the argument very nicely in text, so I'll just give it to you in picture form. Here you've got a space-time, you've got, say, some time-like curves going up on it. S is a space-like surface, and this is its domain of dependence here. And this region's special. This is the region that, if you draw back any time-like curve, it will, by definition here, in the domain of dependence, it will intersect S. So in a way, this is all the stuff that depends in some way on S. It once came from S. We should be able to learn about it from S. And now we consider a little region U. And we apply a diffeomorphism, which is the identity outside the whole region U. It's called the whole region U, and it's not the identity inside. It bends things a little bit. And we construct the resulting space-time M psi GB, GAB. And we ask, does this represent the same situations? We're asking about Leibniz equivalence now. And we imagine somebody saying that maybe they don't represent the same situation. That maybe we really cared about that particular point, and we noticed that, if this was some space traveler, the traveler did pass through that point in one description, and it did pass through that point in the other description. So this is sort of how the argument is commonly described. And so this is a sense of indeterminism. not being as precise as Jim was just a moment ago, but it's a sense in which we begin with some data on S. These are the same. This is the identity on S. And we're considering somebody who might think there's a difference between the future of these two scenarios, and that would be bad. That would be indeterministic. We wouldn't have as good a control over our theories as we thought we had. And now notice, I mean, I just want to say at this point, it's really valuable to have even focused on this representation language. So this is one of the things I learned reading Jim's papers, that it's, you know, the literature's gone lots of different ways, but there hasn't been heavy emphasis on the concept of representation and what's required of it in the whole argument debate. So I found it very helpful to even formulate it in these sorts of terms. It's a question about representation now. So here's our conclusion. It now follows immediately the denial of Leibniz equivalence leads to a very radical form of indeterminism. So conclusion, by reductio ad absurdum, a representation of space-time that denies Leibniz equivalence is an inadequate representation. I take this to be the character of this 1987 paper to establish this statement. So we've got a reductio hypothesis, Leibniz equivalence, and then there's an argument, which is the whole argument, and the conclusion of that argument is that the representation is inadequate. So now I'm going to talk, I think briefly, so we can mostly speak about this stuff in discussion, about the recent paper that Jim wrote on this topic. Very interesting paper now forthcoming in BJPS. So what do we have about these two isometric space-times? Weatherall points out, all right, if we've got two isometric space-times, write them this way, the tilde is to distinguish them. So in the isometry, we'll call it psi. That for any region R of a space-time that may be adequately represented by some region U of MGAB, there's a corresponding region U tilde that can represent the same region of the space-time equally well for all purposes. If there's a guy in the first space-time that you can use to represent something, there's a guy in the second space-time you can use to represent something just as well. And so the argument goes, the reductio can't even be formulated. We can't begin by distinguishing these two distinct scenarios. They were just one and the same from the outset. The reductio can't even be formulated, and in this sense, the whole argument seems to be blocked. Right? These aren't two different things, so we can't even formulate an argument about indeterminism. We can't even formulate the reductio hypothesis. Now, this is just sort of a further comment about this. The fact that, I'm going to talk about this a little bit more in a moment. The fact that such an isometry exists provides the only sense in which the two space-times are empirically equivalent. To assume otherwise would be, now this isn't following this way, I'm sort of picking from a few different points of the paper where we're discussing this sort of view on isomorphism. To assume otherwise would be sort of a misleading use of the formalism of general relativity. It'd be something that's not mathematically natural or philosophically satisfying. It's an ugly thing to deny this sort of view. And I just want to now point out that if you haven't noticed, I mean, the statement in this passage here is very, very similar. It comes apart in some ways, but very, very similar to the statement of Leibniz equivalence. That isometric spacetimes must represent the same situation. Here, though, we're not allowing that it be even formulated as a reductio hypothesis, which we then proceed to argue against. We're saying, no, you shouldn't even say it at the outset. It shouldn't even cross your mind. So, whereas this is Ehrman and Norton's conclusion, this sort of denial of Leibniz equivalence leads to an inadequate representation. Now we're sort of taking much earlier in the argument, sort of as one of the premises, the representation of space-time that denies Leibniz equivalence is an inadequate representation. So why do we do this? The first part of Jim's paper has this very interesting discussion of what sort of thing a general mathematical representation should be like. And again, this is what I take to be a very nice point of discussion that's new to the whole argument, to focus on the concept of mathematical representation and what's required of it. So in particular, isometric mathematical models, isomorphic mathematical models of physics, quite broadly, in Yang-Mills theory and general relativity and in any other context, should be taken to have the same representational capacities. I even find this word very helpful. Now, and maybe I'll just mention the phrase in the beginning. When one talks about expressive capacities, I take that to be, yeah, that's a very, if representational capacities would just have said expressive capacities, I think I wouldn't have ever been bothered by this. So, but I'm worried about this statement as it is formulated. Okay, now, I'm going to try and unpack this a little bit more now, this passage. A difficult thing that I glossed in the beginning is that, well, maybe this is what makes it interesting. There's really two different views you can read off of this passage. There is a corresponding region that can represent the same region of space-time, but then there's this for all purposes, which sort of allows for two possible readings. So let me just identify one possible reading, which will be just ignore that for all purposes altogether right now, okay? Just drop that off. Consider this reading. Isometric spacetimes can represent the same region of spacetime equally well. I mean, this is maybe something close to spacetimes having the same expressive capacities. Consider this example. I've got two portraits. They can represent the same thing. Surely it's not the case that they must represent the same thing. I could identify, for example, so this is supposed to represent Kurt Gödel. Can you tell? That's my crappy attempts to have a go at Gödel. Gödel could have been sitting in this room and I could have said it represents him. But in particular, I could have done it in such a way that I was sort of paying attention to the orientation of Gödel. That this one is sort of oriented in the same way as Gödel is, whereas this one's upside down. There's various things I could use to bring them to come apart. Or I might take one to represent the photograph I've got of Gödel here on the table, and the other one to represent Gödel himself. I can sort of do what I want with representations up to some sanity requirements. Here's another example. So this is why I call this a curious example. There's some funny examples of representation. Take a half plane and consider a subset of itself, a subset of the half plane. There's an isometry from here to here. You see, there's infinitely many isometries, right? I just translate up by some fixed amount, and well, it's just another copy of the same space-time. I guess I'm taking this to be the Euclidean metric, all right? So something that's translationally symmetric. Now, of course, these two space-times, this one and that one, can represent the same thing, but they need not. If it's one in the space-time, they in general don't. I'll have one space-time representing, the half-plane that I live on. I live in some world with a half-plane. And it's different to be standing here than it is to be standing there, okay? And now this is starting to get closer to this example. I've got two space-times. They're isometric. They can represent the same thing, but they need not. And I'm just going now with this interpretation, W1, okay? That's isometric spacetimes can represent the same thing, but they need not. From this perspective, the whole argument isn't blocked, it seems to me. We have two spacetimes that, sure, they can represent the same thing. I've got some state of affairs, but especially once I've identified this one as, say, being the entire universe, the way it is according to, somebody's perspective of space-time. And then I ask, what about this slightly perturbed universe? Perhaps they need not represent the same thing. And so I could formulate this whole diffeomorphism and formulate this this indeterminism argument. This is as Herman and Norson do. So I don't have a real problem with this claim. I think that this is all right, but I don't see that it blocks the whole argument. At least not in the formulation that I gave it. Maybe some of Herman's earlier formulations are a different matter. All right, but let me just briefly then consider this other formulation. You could take this for all purposes more seriously. And I think the first time I read this, I took this very seriously, because this is sort of the crucial juncture. So suppose it's the case that anytime I've got two isometric spacetimes, they must represent exactly the same thing. And maybe this would be a case of a more general claim, that anytime you have two isomorphic mathematical structures, they must represent the same thing. That seems to me implausible. Here's now W2, isometric spacetimes must represent the same region of spacetime equally well for all purposes. This does seem to block the whole argument, because now we're saying, look, if they're isometric, then that's the end of the story. They must represent the same states of affairs. But it doesn't seem to be true necessarily. I gave this example as just one example of many. There are two isometric things that by my definition, they don't represent the same thing. Now, one could point out, there's some interesting extra information in here that's sort of making this work. This is a subset of that, and subset relations aren't being included in this description. But of course, there's lots of things missing from almost every representation you've ever written down. When I drew that picture of Gödel, you might have recognized it as Gödel. And you said, yeah, it's a representation of Gödel. You didn't say, well, no, but it's missing his sort of shoulders and bust, it's not a representation of Gödel. Many representations are perfectly adequate for their purposes and are missing some information about the structure itself. This is how things can come to represent, can be isometric and come to represent different things. Lots of other examples one could give. I mean, this is just one that's current and matters. Here's a conformal diagram from Hawking's original description of an evaporating black hole. People interpret what this represents in radically different ways. I mean, this is a classical relativistic space-time, but we normally take this to arise out of some sort of scenario in quantum field theory on that curved space-time, or more precisely, there should be an underlying phenomenon in quantum gravity that gives rise to this result. And people just have vastly different opinions about what that underlying phenomenon is. Nevertheless, if I point to a black hole, I can use this space-time to represent it. Just as I can use Schwarzschild space-time to represent the black hole at the center of the galaxy, or around, some collapsed star, or many other things. So these examples are sort of curious. In some sense, they seem to be cases of incomplete representation. But I take it this is an essential part to how mathematics comes to represent the world. And I think this is really only for those of you who think about this stuff already. I'm not going to explain this in detail, but if you've ever thought about the Ising lattice and how von Neumann algebras come to represent the Ising lattice, you remember you start with a bunch of fermions in an infinite lattice all pointed to spin up, and you generate all the other states in the basis by flipping a finite number of fermions down. And you do it this way because there's an important mathematical constraint that your Hilbert space have countable basis. And you get into trouble if you go to a countable basis. But we know from the outset that we're losing some states, some important states. We'll never have in this description the Ising lattice with all the particles spin down. It doesn't mean it's not possible. And most importantly, it doesn't mean that the lattice doesn't represent a spin chain. That the mathematical model doesn't represent a realized spin chain. It just does so incompletely, as almost all our mathematical models do. So the take-home on these two interpretations, as I read them, W1 fails to block the whole argument that just can represent the same thing when isometric. W2 seems to be false, that they must represent the same thing when isometric. Of course, we can ignore Leibniz equivalence anyway, and just forget about it. And a little quietism I take to be desirable, but I won't steal all these thunder if this is where we're going. But I do think that too much quietism, we might miss something philosophically interesting. Now, as far as expressive capacity is concerned, I mean, just thinking after listening to talk, that seems to me to be a lovely alternative. One saying, given this language, here's what I can say with this language. Given an image of Gödel, here are the sorts of things that the image can represent. It doesn't represent the magnification of his glasses, or so I can make sort of no claim to that image about that magnification. So it has limited expressive capacity. I find that perfectly reasonable. But I wouldn't want to place restrictions on what that image can represent. That it can't represent two girls with different capacity, lens capacities or something like that. That's all I want to say. Advertisement for the two papers. Thanks.